phrases should not be used when writing a conclusion. So when I see the word accepted, then I know that does not belong in any explanation of the test hypothesis. We said that so many times. We do not accept anything. So fail to reject the null hypothesis is okay. The null hypothesis cannot be rejected. That's okay. All of the above are correct ways? No. Okay? So even this one is wrong, right? So these are correct, but this one has. So I cannot accept anything. When we draw conclusions, we either reject or fail to reject. We don't accept anything. Good. Good pick. Anything else? Do we want to pick anything else? Anyone? Are we okay with everything?
I was looking for a good question that isn't easy, but I think we can move on if everyone else is ready.
Well, did you find something, Sean?
No, I only looked at a few more, but they're simple enough.
Okay, anyone else would like to pick anything, or we go back to the plan for today? So finish up chapter 10. Okay, I'll stop sharing then. If you find anything, I can stop and go back. That's not a problem. Okay, today we're trying to finish chapter 10 with the same thing we've just done for proportions, but now we're working on population mean. And the only difference between the two situations are the assumptions, or what I need to test. That's different. Of course, independent observations is still the same. A sample has to be from a simple random sample, and the normality. But I also have here outliers as well. So pretty much same idea. And this time we're going to use the t-test. That's the only difference. So 10.3, hypothesis, testing about, this time, mu, population mean. Okay, so the only difference is that in P, we used Z statistic, but now for mu, we will have to use the T statistic, also called T0 in your book. The reason why I don't like to use T0 is because it could be confused with P0. P0 is, or mu0, which come from the population. T0 does not come from the population. That's why I don't like to use it. I like to use T statistic, which clearly states that it's coming from the sample that I determined or I collected. That's why I don't like this notation, but it's fine. Okay, so as we know from a long time ago, from confidence intervals, because we do not have sigma for the population, is not known. So we're going to use S, and we have to divide it by the sample size, and we know that this has n-1 degrees of freedom. And because the sampling distribution of x bar, we know that it's approximately normal with mu and S over the square root of n, because we do not have sigma. Okay. Everything is the same. We're just using this time the t distribution. Nothing new, so to speak. Okay. So sample has to be obtained from a simple random sample. A standard deviation is not known. We are using the t distribution with n-1 degrees of freedom. Make sure that there are no outliers and the population is normally distributed, or the sample size is over 30. So a lot of questions over the years, they came up with this 30, realizing that if it's beyond 30, we really don't have to worry that much about the underlying population being normally distributed, as long as it's more than 30. And of course, independent observations. Okay, so let's start with our first example. The mean height of American males is 69.8 inches. So this is known as being mu, or 69.5 inches. The heights of the 43 male U.S. presidents, Washington through Obama, have a mean of 70.76. So this is our X bar, 78, inches. And the standard deviation of S for the sample, 2.77. Sample size, 43, more than 30. Treating the 43 presidents as a simple random sample, determine whether there is evidence to suggest that U.S. presidents are taller than the average American male. So we are using alpha 0.05. Like before, we have to test. We have the null hypothesis and the alternative hypothesis. So mu equals 69.5. We are asked to test if there is evidence to suggest that they are taller than the average American male. Can anyone give us the alternative hypothesis here?
That it's greater than 69.5.
Which, very good. Immediately I draw my picture. Great job. Now I have to discuss the conditions or assumptions. The sample is obtained using a simple random sample. They are telling us to consider it. They are telling us to consider that as a simple random sample. So we have to take that into account. Is this a simple random sample of the entire population? No, it's not. But they are asking us to use it as a simple or consider it a simple random sample. Fine. The population is normally distributed, N is more than 30. Fine. Independent observations, of course. How do I know? Because 43 is definitely less than 0.05 times 30, 360 million. Definitely. So this is independent. At this point, I have T equals. We will not calculate. We don't need it. I'll show you with the calculator. So, but I need you to see it. So it's X bar minus mu divided by S over the square root of N. So X bar is given to us as 70.78 minus mu 69.5 over standard deviation 2.77 over the square root of 43. The calculator will give us this number. So go to stats, go to tests, and select number 2, t-test. And press enter. We are using not the data, we're using the stats. So mu sub 0, yes, so 69.5. X bar, 70.78. Sample standard deviation, 2.77. Sample size, 43. And it is, the alternative is greater than 69.5. You know me, I prefer draw because it gives me the picture and it gives me the p-value and it gives me the test statistic. So this is TST. And the degrees of freedom are 42. So T statistic or T0, whatever you want to choose to use. Here it comes. I don't know why that, I have to change something there. With the color or something is. So the p-value that I got is 0.021. T statistic, the the calculator gave me, and you'll tell me what it gave you, 3.0302. And the p-value is 0.0021. So the test statistic is definitely this number, false for sure, in here. How do I know? Because this is the p-value right here. Just this piece. This is the p-value. What do we conclude? What is our conclusion? Can anyone give us the conclusion? Anyone? Anyone? No one wants to give it a shot?
So the p-value is less than the alpha.
And we conclude?
Statistically significant?
Say it again.
Is it statistically significant?
Yes. So we say we reject the null hypothesis. There is sufficient evidence to conclude that they are taller. And is statistically significant.
What would a type 1 error be for that?
The for any test, this is a type 1 error. Whatever you select.
I see.
Whatever you select is always, when you reject the null hypothesis when it's true. Fail to reject the null hypothesis when it's false will be alpha, will be beta. But this is always chosen. And we have to live with it.
Okay, thank you.
Thank you. Perfect. Very good. Well done, both of you. Thank you. Next question. The font size of a Snickers bar is supposed to weigh 20 grams. So mu should be 20 grams. Because the penalty for selling candy bars under their advertised weight is severe, the manufacturer calibrates the machine so that the mean weight is 20.1. So his mu0 is 20.1 grams. The quality control engineer at Mars, the Snickers manufacturer, is concerned about the calibration. He obtains a random sample of 11 candy bars. Here it is. So n equals 11. I know the degrees of freedom will be 10. And obtains the data below. Fine. Should the machine be shut down and calibrated? Because shutting down the plant is expensive, he decides to conduct the test at alpha 0.01 level of significance. So he chose a smaller error, smaller type 1 error. Okay, so let's put in the data. You want to do this with StatCrunch, or you want to do this with a calculator, or both?
I'd like to see this one on StatCrunch. You could do the calculator first, though.
Okay.
Like,
So let's enter the data. I did enter it. I had a few minutes today, so please enter the data. If you want me to dictate it to you, I will. 19.68, 20.66, 19.56, 19.98, 20.65, 19.61, 20.55, 20.36, 21.02, 21.50, and 19.74. Okay, so go back to stat. Go to tests. It is a t-test. Before we enter anything, we have to discuss the conditions. So it says a random sample. So the first condition is fulfilled, simple random sample. Number 2, does it have outliers? It doesn't appear to have any outliers, no outliers. And 3, independent. Most certainly 11 is definitely less than 0.05 of the number of sneakers that they produce. Guaranteed. So all 3 conditions are fulfilled. So now in the calculator we are using data, not stats. I didn't calculate the mean of the sample. I didn't calculate the sample standard deviation, nothing. So I'm going to use the data. And the data is coming from list L1. Mu 0. So after we test it, we have to write the null hypothesis and the alternative. We have to decide because we need to know what type of test that is. So he calibrated the machine to have mu equals 20.1. And he's not sure whether this is going to be, he doesn't say greater or less. He only says, what if it's not that? That is the only concern he has. What if it's not what the machine should give? This is what I calibrated the machine for. But what if it's not that? I'm not really interested if it's more or less. I'm interested if I get that or not. So this is a two-tailed test, which splits the alpha in 2. So alpha divided by 2 is 0.005. So this alpha and this alpha, because it's a two-tailed test, so this is 0.005 and this is 0.005. So we are using list L1. We are using not equal to for the alternative. And I'm going to draw. And I will get from, after I finish, I will get T statistic with degrees of freedom, 10. And I will also get the p-value. If the p-value is less than, so if the test statistic results here, I would have to reject the null hypothesis. If the test statistic is a number between these two numbers, then I would fail to reject the null hypothesis, and we'll draw the conclusion in a minute. Okay, so I got the test statistic to be, let me check my numbers. T, of course. Okay, mu 0, 20.1. List L1. Okay, so I got that the test statistic is 1.04. Tell me what you got.
1.0406.
Excellent. And
Same.
I'm hoping you got, like I did, 0.3226.
Yes.
Perfect. So 0.3226, the p-value is greater than alpha, which means the test statistic falls to the right of 0, somewhere here. So it's in the non-rejection region. So we have to say we failed to reject the null hypothesis. There is sufficient evidence to conclude that the machine does not need to be recalibrated. Coming from this sample, there is sufficient evidence to conclude that the machine coming from the sample. When we every time we say there is sufficient evidence coming from the sample, from this particular sample, to conclude that the machine does not need to be recalibrated. It's doing okay. And now I would like to look at two examples concerning